Okay, so today I'm just going to make a quick video about some things in biostatistics that I think will make your study experiences and the USMLE hopefully a lot easier. I think that these are some things that aren't so obvious sometimes, but with a little bit of thought, it can be worked out. So I'm going to try to explain these things in a few different ways. I'll try to use the ways that I felt like really helped me realize what I was doing. Um, so really quickly, I think that you all know the definition for sensitivity is going to be our true positives divided by true positives plus false negatives. So this is pretty much telling us how well a test in itself can find people who truly do have a disease. And ideally, we do a high sensitivity goes a long way because we don't really want false negatives. That's bad. We don't want people to maybe walk away. To walk away from a tuberculosis test or an HIV test with a negative result, appearing negative, a false negative, when in fact they're positive. So we don't want to miss that. Sensitivity is important because we do want it to be high enough, but the question is what happens when it gets to be too high at the same time. So that's where, going off that idea is where kind of this graph comes from. I used to really despise this graph, but it's not so bad if you just kind of like take a minute to think about it. So our x-axis is going to be our test result. Sorry, I know that my handwriting isn't the best. This is just going to be a number of people. So I'm going to do this example in reference to a PPD test for tuberculosis, let's say. Alright, so let's say that over here it's going to be all of our healthy people. Right there, that'll be healthy. People who don't have tuberculosis. And over here we'll do all of our sick people. Everyone that has tuberculosis. Okay. So let's say that right here, close to the center in between them, is where we'll mark off 10 millimeters of induration, on the TB test most of you have had when, they make the bubble. So let's say that you need to have 10 or above that, moving from 10 to the right to be considered inside the sick range. You have to hit that mark or above. So anyone that's, let's say, down here, those guys are going to be our false positives. Because even though they fall under, just follow that color there, even though they fall under the healthy graph, in terms of these people are healthy, they are exceeding our 10 millimeters of induration cutoff. So those guys will be considered false positives. Now we could, of course, just move our cutoff backwards a little bit. And let's say that we want to put it right over, slightly to the left, we'll put it right over here. And that would be 5. Okay, so now if you have 5 millimeters of induration or above, now you're considered as being positive for having PPD. Um, so look, our false positives used to be just past our cutoff there, because they looked like that they were sick when they really weren't. But now our false positives, by moving this line backwards, now we have all these guys that are false positives. We just, by lowering the amount of induration, by lowering the cutoff, we are now accepting more people as having tuberculosis, which makes sense because everyone can get a little bit of an interaction, of a reaction, that is. So, if we're lowering from 10 to 5, we're going to get a lot more false positives here. However, at the same time, since we lowered the cutoff and now it's only 5, we're not just going to be getting a lot of false positives. We're going to be lowering the false negatives. So remember, the false negatives is on the denominator of our sensitivity equation. So if I'm going to lower the amount of false negatives, then sensitivity will go up. A different way of saying that, if it helps, because I know that the terms can get a little bit confusing, is that, if it's only going to be 5, if it's so low that I'm going to be accepting so many people, I'm not going to be, it'll be hard to be sending anyone off who has tuberculosis and saying that you're negative, saying that you're a false negative, when really they're positive, because the 5 millimeters is so low that chances are, if anyone has the disease, we'll accept them. So that's why the sensitivity is gonna increase. So in a way, it sounds like a good thing. Like, yeah, like we will be finding all, like we won't be sending off anyone. But the problem is that look how many false positives we get. Like in terms of epidemiology, that doesn't make any sense. If now we're going to say that in addition to finding everyone who's sick, we're going to say that so many healthy people are sick. So, that's kind of the problem there with lowering it back to 5. I want to make one more crucial point here, because I know that test examiners love to go after this, and that's the point of negative predictive value. So negative predictive value, first I'll start equation-wise, is true negatives over true negatives plus false negatives. So an important way of thinking about how negative predictive value works is, if you tested negative, what are the chances that you are in fact negative? What is the chances that, if we're saying that, hey, you don't have a disease, what are the chances that you really don't have the disease? And that makes sense in terms of the formula. We're taking everybody who is negative, including the true negatives, or healthy people, plus people who were falsely negative and actually had the disease, and we're going to take our true negatives and divide it by that. So we're only looking at people who have a negative result and saying, what are the chances that so-and-so is in fact negative? Now I'm bringing this up now because with our current example, we're finding a crucial connection between sensitivity and negative predictive value. And I don't think that a lot of people really kind of recognize, this crucial relationship. Remember, in our example, we don't have that many false negatives anymore, right? Because we lowered our cutoff rate to 5. So pretty much the whole world, sick or healthy, with such a low cutoff, we're going to say that, hey, you have TB. So we're not really sending so many people away. We definitely lowered our false negatives. What's in the denominator of negative predictive value? False negatives. So I'm going to be decreasing false negatives. Therefore, if I'm decreasing it for negative predictive value, false negatives, then our negative predictive value will go up. If sensitivity is going up, the negative predictive value is going up. And if you don't like kind of the graph way or the equation way of thinking about it, Think about it this way. Again, we're doing the 5 millimeter cutoff. That means everyone with the slightest reaction to everyone who truly has tuberculosis, they all appear positive. So, if pretty much everyone is appearing positive, if you do happen to be one of the few people that actually gets a negative result, with such a strict cutoff, then you probably are negative. And that's what the definition of negative predictive value is. If we really make it hard to send you off with a negative result, if you do in fact get a negative result, then you probably are negative, the negative predictive value. So now I'm just going to kind of spin this, in a different direction, and let's look at what happens with specificity. Now, I feel like for some reason, because sensitivity has a word positive in it, you think that it's like, oh yeah, that's the most important thing ever. But specificity plays a huge role in terms of epidemiology, and we really can't forget about it either. The definition of specificity is how likely is it that a test can find out that you don't have a disease? So ideally, a high specificity is really, really important. Because it is what it sounds like. We want to be, we want to be specific. So if something, let's say that a screening test had a high sensitivity, and we did, sticking back with our TB example, something had such a high sensitivity that something as low as a 5 millimeter induration means that we're going to consider you positive. Now would be a good time to get a very specific test in to kind of filter through those people. So, a great example of this would be what happens with HIV. The initial test is to test to see if you have the antibodies, and that test has they check your blood or your saliva, and that test has a very very, very high sensitivity. It's a very high cutoff. So if you do happen to have those antibodies, then yeah, you will be. Then we're considering you positive. But since the sensitivity can never be 100%, that's where we throw in the specificity test, and that's the Western blot for the actual HIV proteins. So that's just kind of a idea of how we could filter out who actually has it versus who doesn't. Because a sensitivity test will inevitably pick up a few people who don't actually have the disease. So specificity actually has an important relationship to positive predictive value. I really want to point these out, because I don't think that it is super obvious, because these things seem like that they're from different worlds. Like specificity has to do more with negatives, positive predictive value has to do more with positives. But test examiners love asking about these because it really shows if you know your stuff. So positive predictive value looks at, just like negative predictive value, we're looking at after the fact. If you tested positive for something, what are the chances that you are in fact positive? If you tested positive for something, what are the chances that you are in fact positive? That's kind of the key idea there. So let's play around with our graph again. Same thing as before. Let's say that these are our healthy people. These are going to be our sick people. This is going to be our cutoff, right? Sort of down the center. Sorry. Let's say that our cutoff was 10 for a PPD, right? Okay, so now let's kind of play with it this way this time. Sorry, let me mark this as sick people so we don't get confused. Now instead of saying that you need to have a result of 10 or above to be considered positive, let's say that we're going to do 15 or above now. Shift it to the right this time. 15 millimeters, right? Before you needed to be 10 or above, right? So before we kind of had these false negatives, right? Everyone over here. They're on the left side of our cutoff. They still fall underneath our sick graph. Yeah, so they're going to be our false negatives. And now that we're going to push it over to the right, now we're going to get a whole bunch more false negatives, right? So look, that's just going to start increasing, 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 because remember, we need 15 or above. So everyone to the left of 15 is going to not be considered as having it, even though we're definitely, leaving some people out here. So what's going to happen now with the specificity or the positive predictive value? Well, the good news, I guess, is that if you do happen to test positive, again, just think about it. Let's start logically first. If you do happen to test positive, I'm sorry. So we have a lot more false negatives here, right? So if we have a lot more false negatives, people that we're leaving out because our definition is too high, 15 is way too high, we're going to miss a lot of people who actually have it. Are you going to have a lot of false positives? Then the answer would be no. Really, you really won't have that many. You won't have that many false positives, because if you do happen to achieve the 15 or above mark, remember, imagine it as it's so hard for someone to get a bubble length of 15 or 20 or 25. If you do happen to hit that cutoff point, I'm pretty sure that it's more likely that, unlike before where it was 5 and you're just any ordinary person who has a little bit of reaction, if you are hitting 15 or above, you're really swelling, your body is really reacting to the PBD test, then you probably have it, is pretty much how it goes. So that means that our false positives will decrease drastically, right? If we're going to shift it over to 15, there won't be that many people that are going to appear positive. I think that if you're hitting 15 or above, you have it. Same thing here. False positives go down. So if the false positives go down here and they go down here, what's happening to specificity? It's going up. Specificity is increasing. And again, positive predictive value is increasing. So I think that is all I have to say about that. I know that the graphs aren't perfect, but you can always just type in comment boxes for questions and let me know. All right, I'll have a new lesson out soon.